Alright, so 4.2 is going to be about sigma notation for a while here. And the basic idea here is the sigma, big E guy, just means to find the sum. And you're going from I equals 1 to 5. So what that means is you're going to plug in the numbers 1, 2, 3, 4, 5 into this, and you're going to add up all their different answers. Now, for something like this, it's not so bad. 3 times 1 is 3, minus 4 is negative 1. And we add that to plugging in 2. So 6 minus 4 is 2, plus, if you plug in 3, you get 9 minus 4 is 5. And pretty quickly, you're probably going to realize that you're going up by 3's every time it's slope. So then you got 8, and then you get, so 1, 2, 3, 4, and we got to plug in 5 still. So 11. Now when we do this, we can add it up a lot of different ways. But I mean, if you want to pair it differently, um, 1 and the 11 would be 10. That'd be another 10, so 25. That's not so bad. We want to do this one here. You have 1, but you get the idea. Now, what happens here, it gets a little bit crazy when you're asked to do 1 through 72. 1 through 4, no big deal. I mean, I can make this a little more difficult. It gets tedious, but I don't really want to plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 through 72. So we need some better ways of doing that. And the better ways are the formulas underneath here. Now you'll notice that I don't have one for I to the fifth, and you can kind of tell they get a little bit crazy. So these are the formulas that you kind of need to know, at least for this chapter. I don't know if you would need to know like what I cubed is on the AP exam right off the bat. Most of them you're still going to be able to use your calculator, but for us to be able to prove some of the stuff we're going to see in the near future, you kind of need to be able to do a couple of these at least. So here's the basic ones. If you want to add up C, now you realize there's no I here. So if we're doing the sum of 3 from 1 to 5, you're just going to have 3 plus 3 plus 3 5 times. So C times N, 3 times 5. If you've got just I, so 1 plus 2 plus 3 plus 4 plus 5, that's just the last number times the last number plus 1 divided by 2. Okay? And then you get more complicated formulas, and you can prove these with something called mathematical induction, which you show that they work for a couple of them, and then assume that it works, and show that it will work for the next one. It's kind of a tricky one, but you can use it to prove any of those. All right, let's try to use some of these formulas. All right, so this definitely not something I want to do by hand, or without the formulas, but hand's not too terrible. So we're doing 52, 1 to 52. Now you do realize that all of these start at 1. If they start at 2 or 3, it's a little bit different. You got to kind of modify the formulas a little bit, or just kind of take into effect stuff that you're missing, subtracting them out from the answers. But since it's from 1 to n, we can just plug these in. And you have to realize there's 3 pieces here. I'm going to treat them as 3 separate things. Other things that you can do is you can pull out constants out front. We didn't really talk about that yet. But if it was a 1 here and a c out front, well, you'd have c times, well, 1 times n, it's just be c times n. It would still work. It's really just a distributive property in action. So that 5 there is not going to cause us too much trouble. So I use this one. It's going to be 52 times 53 divided by 2. That's really all the first one would be. Minus 5 times, well, the I squared, which would be 52 times 53, and then the last one's a little bit trickier. 52 times 2 plus 1, so 104 plus 1, 105. Divided by 6. And then plus 4 is a constant, so c times n, 4 times 52. Now, to tell you the truth, I probably would just pull out my calculator to do this anyway. I probably could figure out what these are if I had to, but I would just type this in my calculator and get the answer in the end. So I'll show you doing one of that one time, and I'll also show you how you can do it on the calculator to check it too. So on the calculator, this is a little bit of a pain because the second I bring up my calculator, that stuff's going to erase. Alright, well, you can check this on the calculator all you'd like to. I'll let you do that, and I'll show you on the last one kind of how to do it in the calculator the quick way, just how to check them. Alright, so the last one here, this is a constant, it's just going to be 500 times 3, or 1500. We can do that one real quick. For something like this, you don't want to do like a product of two things, just distribute it. And you have 3I to the third minus 4I. It's going to still get the sum from I equals 1 to 15 up front, so it's 3. Then you got to use I cubed, so 15 squared times 16 squared over 4 minus 4 times I, which is n, n, which is 15, n plus 1, which is 16, over 2. Alright, so if I want to figure out what that is, or if I want to just find the answer to this, or if I'm allowing you to just kind of come up with an answer, you could, in your calculator, basically just do this. Now, if you get the new operating system, it's fantastically easy. You hit alpha window, and then go down to number 2. And then you just make it look like however you want it to look. I would suggest using x's, since the variable doesn't matter. X equals 1, not 11, just 1. And we go up to 15. And then we write our equation. X times 3x squared minus 4. And then you hit enter. That's really it. Just make it look how you want it to look. Again, that was alpha window. Enter, and you got your number. Alright, so the whole goal from this is to find the area under the curve. So to find an area under the curve, you gotta imagine some sort of curve. And this is our f of x. What we're going to do is we're going to break this up into little rectangles. And actually ours are going to be particularly right-sided rectangles. Now you can do left endpoints, you can do right endpoints, you can do midpoints, you can do trapezoids, all that fun stuff. But the idea is we want the actual area under the curve, not the approximate area under the curve. We want the true area under the curve. So what we have to do here, as you can see, if I draw these little rectangles here using the right endpoints, I get some error. You know, all of this right here, that's all overstepping my bounds, right? Oh, that's error. If I use a left endpoint, I'm still going to get error. But the idea here is we want to make these really, really small little rectangles. So tiny that the error basically becomes 0. So what we want to do is we want to slide this with a small change in x and make it more along the lines of dx. So all of these rectangles we're going to talk about, we're going to slide the width down to nothing. And if we can slide that width down to some small, tiny, infinitesimal change in x, we won't have any of this extra area of the extra error. We'll just have maybe dust up there that really won't count to anything. We will get the true area of the curve. So, how many rectangles is it going to take? Well, it's technically going to take an infinite number of them. Alright, the formula is actually very easy. We want to add up all the rectangles, so that means we have to do a sigma from I equals 1 to, well, technically you shouldn't really put an infinity symbol over here. We're just going to go to n. Okay, so that's going to add up all of our rectangles, n rectangles. Alright, and we need a width, dx, a small change in x, dx, and we need a height. Well, that's our f of x. The problem is I can't just do x. I'm going to need x sub I. That's going to be, x sub I is actually going to be the hardest part. It's going to be a right endpoint. Now you can do this with a left endpoint, but right endpoint is generally actually a little easier because you're going to end up adding 1 to each of these. Adding 1 to the first one. This will be your 1. You don't really want to start this at 0. You want to start at 1, so meaning 1 endpoint to the right. Alright, and then your d of x because you're always going to do this on some interval. You don't want to do the infinite area of the curve. We'll talk about that later on. We're doing it from A to B. So we're going to take this width, b minus a, and we're going to cut it up into n rectangles. So your distance here is the total distance from A to B, and we got to figure out how many rectangles we're cutting this up into. So dx is going to be b minus a over n. So take the width and cut it up into n rectangles. Alright, so that's the basic thing. And once you have all of this done, you're going to take the limit n as n goes to infinity. We're going to ratchet up the number of rectangles, because n stands for number of rectangles, into infinity. But you can think about this, you take the limit of some number divided by infinity, it's going to go to 0. Dx is going to go to 0, which makes you want to think that all the little areas are going to be 0. But it really doesn't work that way. You end up getting some area from each of the little rectangles, and they will add up to the exact area under the curve. Alright, so let's see how that works in the end. Let's move this down a little bit here.